Hello, everyone. Thanks for joining us. We're glad you could be here today. My partner, Ariana, and I are excited to present to you our work at Hohonu, building pipelines and platforms for remote marine data. And before we begin, we'd like to give a big thank you to the 11th Hour Project for all of their generous support and funding, which makes projects like ours possible. So what exactly is Hohonu? Hohonu is an early stage startup based in Hawaii that manufactures low-cost and reliable tidal sensors. You can see a photo on your left of an early sensor prototype. And the way these sensors work is they're placed at a fixed height above the water, usually on a dock or a bridge, and they just ping the water below in order to measure the distance from the sensor to the water surface. And that's how they measure the water level at that location. This particular sensor was deployed at Hereia Fishpond in Hawaii, just off the coast of Oahu. The second aspect of Hohonu is the data science aspect, and that's the part that we're most excited to talk to you about today. Our mission as data scientists is to take this raw tidal data and pre-process it to present it in a clean way to our users, as well as present our users reliable and accurate tidal forecasts for every sensor that they have. And before we jump into the meat of the data science, we want to give you an overview of how data flows through our pipeline. So the first and most fundamental component is, of course, the tidal sensors. These sensors are streaming raw data continuously, which is uploaded to Hohonu's internal company servers. That data is made accessible to us at the Data Institute via public web API. We query the data and do all of our pre-processing in Python, as well as our time series forecasts. We save the clean data and forecasts to an Amazon S3 bucket. From there, we are able to load that data into a Postgres database running on Amazon RDS, which serves as the backend for our web application. Our web application is based on the Django framework. We deploy it inside a Docker container, which runs on an Amazon EC2 instance. So what does all of this give you? All of this gives you a comprehensive dashboard of tidal readings and forecasts. You can see a snapshot of that dashboard before you. This particular plot is of the water level at Hereia Fishpond, which you saw a couple of slides ago, and it has three different components. In the dark blue on the left, you can see the tidal level at that location as recorded by a Hohonu sensor. And on the right, in the light blue, you can see a forecast generated by our time series models for the first few days of June. And on the left in orange, you can see our historical forecasts. And we always save our historical forecasts in order to judge how accurate our forecasts are. And that accuracy is summarized in the table to your right. It shows the average prediction error for the 1 day, 3 day, and 5 day forecasts. And the way you would use this is if I wanted to use the forecast for, say, June 1st, and I was only interested in the 1 day forecast, I would look at the table and see that the average prediction error is 17 millimeters or thereabouts. So I could be confident that for the 1st of June, our forecast, the Hohonu forecast, is off at any given time by at most 17 millimeters.
So now that you know a little bit about what Hohonu provides in terms of tidal predictions, you may be wondering, well, who does this actually benefit? According to the National Oceanic and Atmospheric Administration, about 40% of the nation's total population lives along the coastal community. So with climate change causing sea levels to rise, what we have here, we now have that during high tides, these tides are extending further and further inland. And this is a problem that we expect to be happening more often as we progress into the future. And this image here is just an example of what this tidal flooding looks like in these communities. So with the Hohonu tidal predictions, we now have an early warning system for the governments that monitor these communities so that they can better prepare and alert the people that they care for. And you also have the other individuals like the Hawaii fish pond farmers and other businesses that rely on harvesting fish for a living. They also pay close attention to when the next high and low tides occur, so they know when to go out and cast out their nets. And lastly, the group that can benefit from this is the research community, the community that is actively monitoring how exactly these aquatic systems are changing due to climate change. They can now purchase one of these sensors, take a look at the data and the predictions that we provide so that they can further extend the research in this area.
Some of you may be familiar with NOAA, the National Oceanographic and Atmospheric Administration, and be thinking to yourself, Hohonu is a bit similar to NOAA. I mean, they both provide tidal readings and forecasts for a variety of locations. So how exactly is Hohonu different? Well, there are two main components, one hardware and one data science component. On the hardware side, our sensors are much cheaper, an order of magnitude cheaper than NOAA sensors. You can see on the photo on your left in the red box is a latest generation Hohonu sensor. You can see it's very small enough to hold in one hand, and most importantly, it's easy to install. I could install it, you could install it, and be done within an hour. In that same photo in the background, you can see the tall tower is a NOAA sensor, and you can see it's much more industrial in scale, and as a result, it's more expensive. So why do we care about manufacturing low-cost tidal sensors? Well, low-cost sensors make coastal coverage possible at an unprecedented scale. For example, South Carolina could place, for the price of having one NOAA tide gauge in that one location, could place a Hohonu sensor every 18 miles along their coast. The second part in which we differ is our data science models. So we use a VAR model for our time series model to generate our predictions for every tidal location at which a sensor is deployed. And we have found that over all of 2019, our forecasts are on average 40% more accurate than NOAA's forecasts. And the plot on the left just shows you an illustration of that. The plot on the right is a little bit more interesting, and I want to unpack it for you. It shows the distribution of errors for both the Hohonu forecasts in light red and the NOAA forecasts in light blue over all of 2019. So it's just a histogram of the error, and the x-axis is the error in millimeters, and the y-axis is just how many times that error has been observed over all of 2019. And you can see they have two different shapes. So let's start with the Hohonu shape. It has the shape of an exponential distribution. And if you don't know what that means, don't worry. I just want you to think about waiting for a bus. If you were to sit across from a bus stop and just with a pen in hand, record how long every person has to wait for the bus, you would realize that the waiting times sort of follow this exponentially decreasing shape, because most people don't have to wait that long for a bus, although there are a few people that have to wait a long time, and it always feels like you're that one person. On the other hand, if you look at NOAA's distribution, you see it follows a much more traditional normal distribution, a bell curve, and the errors are much spread out and cover a larger scale. So for Hohonu, you can see most of the error bars are very close from 0 to 50, just like maybe waiting for a bus would be from 0 to 5 minutes. So this just means at any given time, you're more likely to observe a Hohonu error that's between 0 and 50 millimeters than something greater than 50 millimeters. NOAA's observations, on the other hand, those errors are vary over a larger range, and the mean is somewhere probably around 70, 75 millimeters. But also, you can see errors up to going as far out as 250 millimeters, although they're not as likely.
Now you're probably wondering, how is it that you're able to achieve more accurate predictions in NOAA? And that's because of two things. One, we use an entirely different model. More specifically, we use a vector autoregressive multivariate time series model. Two, we form what we call sensor communities. What we mean by communities here, we just mean grouping sensors together based off of similar tidal patterns. In this example that we see here, this is a community for sensor 46. And as you might have guessed by now, this purple line here, this sensor wouldn't belong to the community for sensor 46, but these would. So when we want to make future tidal level predictions for sensor 46, not only would we feed it its own data, but we would also feed it the data of all the sensors that belong to the community for sensor 46. In the previous slides, we saw that these low-cost sensors actually have the ability to make very accurate predictions. A big part of that was also due to us identifying anomalies in the data and then imputing them right before we make our predictions. And before we can do all that, we started off with one question. Can we distinguish hardware anomalies from anomalous weather events? the first step into answering this question for us was being able to create a system that would automatically detect data as it's coming in and tell us whether it's anomalous or not. Right now, our system can identify both the hardware and natural anomalies. More specifically, the hardware can be broken up into two kinds, one being the flat line and the other being the random spikes that we noticed in the data. For example, the flat lines can happen for different reasons. It can happen when a sensor becomes decalibrated, or like other sensors that Hohonu also provides that go in the water. Over time, these sensors will develop algae and then slowly flatline, indicating that they need to be clean. The other anomalies that we're very proud to say that we're able to capture are these storms and tsunamis. Although tsunamis don't happen very often, but in 2018, this mini tsunami happened here in Hawaii, and we were able to capture it. Some future directions that we have is, now that we have this system in place that can automatically detect and tell us whether data is anomalous or not, we need to be able to say then, okay, this data that we see here is a hardware-induced anomaly, and this other data that we see here is actually a storm that's occurring. So being able to classify and distinguish between the two. The other thing that we were thinking about was incorporating new variables into our models. Hohonu also captures information like wind, temperature, salinity. So we hope by incorporating these new variables into our models that it would give it a better sense as to how the environment was like when this water level was recorded. And before we end our talk, I just want to say a big thank you to the 11th Hour Project, the Data Institute, for allowing Matt and I to work on this very environmentally impactful project. And we also want to say thank you to Daniel Grisenda at the Data Institute, Brian Glazer, and Stanley Leo at Hohonu. Thank you.